Much like Icarus flew too close to the sun, I too have flown so far and high that the wax of my wings has melted, and I am plummeting down to earth. As the seas and mountains around me rise, I can no longer see the line where the sky meets the sea. For a moment I was free, and I could see the beautiful fields of Crete in front of me. But now I return to the earth, where an endless slumber awaits me. Yep, that's right. In the end I couldn't perfect this effect, but I'll show you where I got to and explain what needs to be done for it to be complete. Quick shout out to everyone who's been watching my videos so far and leaving such great comments. This started out as a way to keep me sane, but the feedback has been so positive I'll definitely consider continuing. But enough personal rubbish. Let's get into the nitty-gritty. We've two cool versions of this effect, but they're not efficient. They got the beat and the rhythm, but they lack the grace and the poise. I'm sorry to tell you this, friends, but the only way forwards is to get technical. Unity's scriptable render pipeline is a barely supported, undocumented, infuriating bucket of fine. It's fine. It's fine. Writing this video was incredibly stressful for me because I had to be sure that the version I presented to you was as efficient as possible. And guess what? I know it's not! Nothing infuriates me more than watching someone write bad code for 5 minutes, but I've lived long enough to see myself become the villain, so here we are. I especially hate it when they dance around the topic. My new favourite window in Unity is the frame debug window. I don't know if you've ever read that article about how Metal Gear Solid 5's Fox engine breaks down a scene, but it's essentially that. It separates the processes of how the scene is actually rendered out, all with neat feedback from the screen. And it's the perfect tool to tell you how we're going to do this effect. See, we're going to try and insert our own stuff right here. Or here. Ugh. Quick history lesson. So, Unity had its own built-in rendering pipeline for years, until, naturally, developers started crying for more. Since the source code for the engine is very controlled, your average farm-grown developer didn't have access to any of the lower-level rendering. Therefore, the scriptable render pipeline was created. Then, to demonstrate how powerful this was, they used the new system to create the lightweight render pipeline and the high-definition render pipeline. And then they changed the name to Universal Render Pipeline because lightweight had negative connotations, I think. Now, this shift to scriptable rendering is not a unanimously supported decision, with several outspoken members of the dev community accusing Unity of making new core systems in the interest of pleasing shareholders, and never spending the time to focus on optimizing the systems they have. Other people like the new systems, and think they're absolutely necessary if Unity is to survive in an ever more competitive market. I'm of the group of people that don't have opinions of things they know very little about, an increasingly small portion of the internet. Anyway, the important takeaway here is that we can take one of those pre-built render pipelines, in this case URP, and use Unity SRP to add and change things. Specifically, post-processing. Well, kinda. Unity had its own scriptable post-processing stack back when it was built in, which was then later replaced with post-processing v2, which used command buffers and is the subject of the discussion today. URP currently uses its own newer post-processing stack, but it is currently uncustomizable and therefore worthless. But our effect isn't technically post-processing, as we're not doing anything to the final image once it's been rendered, but rather changing the rendered image of a completely separate layer and integrating it into our scene. So it's sort of peri-processing. That sounds fun. Specifically, I'm going to get our forward renderer that has been generated for us and add a render feature. These are experimental, mind you, as is essentially all of SRP. It's all still in active development, subject to change, and as we will discover later, missing key features. Our URP render pipeline is made up of several passes, each one dedicated to a different kind of thing to render. Let's quickly go through them now. Shadows. Gotta figure out where those shadows go, get our light maps and projections done. First things first, pre-passes. Let's gather up any information we need before getting into the nitty-gritty. Depth stuff, LUT stuff. Maybe clear the screen, I don't know. Opaques. These are our big boys, all our walls, pots, and loot boxes. They're totally there, and you cannot see through them. They check and write to the depth buffer, which I mentioned in the last episode, allowing us to figure out what cuts out what. Skybox. Let's look at a depth texture. Huh, that must be really far away. Guess we should just replace it with some sky. Yeah, that looks right. Transparent. But sometimes we've got to see through stuff, so we render it last and put it on top of what we want to see on the other side. These guys check the depth buffer so they can cull the right bits, but they don't write to it as they don't block anything from view. They are also the bane of my existence. Post-processing. I already said that. This is the cool stuff. Everything's rendered out so we can add some bloom or color grading or whatever. That's really neat. So, adding a render feature will execute its own pass into the pipeline wherever we want it. There's only one type of render feature currently available, and it's called render objects. It allows you to render specific objects at any point in the pipeline, change their material, or even the camera settings they're rendered with. Very useful for FPS weapons. The knowledge I'm presenting today is based off using the scripts behind this feature, reading up on the documentation, as well as really stellar tutorials by people like Catlight Coding, link in the description. There's honestly not a lot out there on this stuff, so I hope that my basic explanation will allow you to take it further and do your own stuff with it. Here's the basic outline of the render feature that I've coded. The first thing you have to do is inherit from the scriptable renderer feature class. If you don't understand what inheriting is, then that sounds like a you problem. No, but seriously look up object-oriented programming. Essentially, we're taking all the deliciously goodness of a class and we're going to add and change some things. You've got your serializable settings. These can be changed in the inspector, which is always going to be useful when you want to test out the effect. You can change things like what materials are used and, more importantly, when the pass is supposed to occur in the pipeline. We initialize these settings with our basic feature pass. This is another class that we'll write in a separate file, but for now, initialize it in the overrided create function. Then, you need to add this pass to the queue in the overrided add render passes function with these parameters. Very simple skeletal class, which as you can see is a lot more complicated in the original render objects version. Then, in our basic feature pass class, we inherit from the scriptable render pass. The scriptable renderer feature and the scriptable render pass classes are the backbone of the scriptable rendering pipeline. And while it's annoying to say scriptable so much, it's more annoying that there are 3 different forms of the verb to render in there. Here we declare some variables. We've got our customizable parameters for the pass, as well as a bunch of things that are 100% necessary in order to render out our objects. The profiling sampler lets us see this pass in the frame debug menu. The render state block tells us what we want to write when rendering. The shader tag ID lists allow us to specify which passes to call in shaders, and the filtering settings allow us to control which objects and layers we're planning on rendering. Finally, we've got some static IDs that we'll use during the pass itself. Just easier to set them here than calculate them every time we execute. Then we set up our constructor exactly how we called it in the basic feature script. Important thing to note here is the render pass event. Here we're assigning the variable from the inherited class that tells the pass when to execute. Everything else is just setting up basic values and using the settings from the inspector. The final part, and holy grail of this class, is the overridden execute function. This function is what is executed when it's time for this pass to actually do something. Here we've got our command buffer. We're going to give this baby a series of instructions, or commands, and then jam it into our rendering context and tell it to execute. Each time the command buffer must have a render target where it's going to send its information. It can also create and release temporary render textures that only exist in memory during the pass. I've got this set up to essentially recreate the pixel art effect from the previous video. Recall that we used 2 render textures, one for the rendered out pixelated color and one for its depth. We used the command buffer to create these temporary render textures with this code, use this code to make them the command buffer's render target, and then make sure they're wiped so that they contain only transparent data. Put in the context and clear the command buffer for further instructions. Next we need to render what's on the screen onto the render textures. Since they're still the render target and we've already given it a layer mask so that it only renders the pixel layer, we just have to call the draw renderers command with the information already given to us for this to work. Now we've filled our render textures with pixely goodness, but we need to actually send this to the screen. Since this is a new render target, we can carry on adding commands and don't need to execute yet. This is more efficient. Probably. We got to set our new render target to the pipeline's temporary render texture, underscore camera color texture, something that can be accessed by every shader and is directly drawn to the screen at the end. Then we got to do what every post-processing stack has had to do since the dawn of time. We have to blit, which is a word that stands for something. Blitting essentially means that we're taking images and we're either copying one to the other or blending them together by essentially rendering a square with a special shader that takes the first image as an input. Anyone who's anyone in computer graphics will tell you that squares don't exist and are just 2 triangles, so it's technically more efficient to use a big triangle and ignore the tips, but that's too complicated for this tutorial. So we give the blit command the identifier for our pixelated render texture, tell it that the render target is the one we already set, and give it our special material with a special shader for rendering. Then we release our temporary render textures and do our final execute to wrap it all up. But we're not finished because we still have to actually write the goddamn shader. And at this point we're 3 levels deep and you can see why this is the goddamn advanced tutorial. Thankfully, the shader is essentially just a coded version of the shader graph I made in the last video. Here we're sampling the depth, here we're making a stable filter, and there's some bonus stuff to make sure we're getting the right depth of the outline. You could probably use a shader graph for this, but even if it did work, it'd be hella inefficient. Even though it's scary to learn HLSL and Shader Lab, it's definitely worth it for that low-level functionality, and there are some great tutorials out there. An important thing to note are these 2 tags. The blend tag allows us to dictate how the rendered image is blended together with the destination image. In this specific case, it's using the alphas to essentially paste on top of our destination image like so. The Z-write tag allows us to stop it writing to the depth buffer, because if it did, it would write the squared's depth and the depth buffer would just be a useless plain color, losing all of our information. So we need our custom render pass to execute before we've rendered our transparents. Good stuff. Let me just set it there, and boom! We did it! We've completely reproduced the effect in SRP. We are gods! The laws of graphics are ours! Nothing can stop us! We shall fly higher and higher until... So, this effect and the one in the video previous sort of break down when you add transparents. Since transparents don't write to the depth buffer, there's no way to account for them after the fact. But because they cull by reading from the depth buffer, they won't account for our pixelated objects. So the solution is simple. We're rendering out our pixely boys before the transparent, so we just update the depth buffer with our new values. Well, we can't. Or at least, I can't. Hello and welcome to 8 weeks in the future. Everything is worse now. Links in the goddamn description. I'm sorry, this video has been a giant slog to get through, so I'm going to cut to the point. In doing further screenshots for the final part of this video, I came across a 6-year-old Reddit thread that led me to the exact answers I was looking for. A way in HLSL to modify the def buffer. I've changed this method and only this method, and now it works like a dream. Enjoy this insurmountable trilogy of videos. If I ever make more, they'll be less tutorial-y. I think. Who knows? Would you believe that this solution is not only so well known that it's baffling it took me 2 months to get here, but people actually advocate not using it, as changing the def buffer of pixels after they've been Z-tested can get a little nuts. Luckily, I know what I'm doing and this is fine. Probably. I'm working on my first commercial game now. I love my girlfriend. See ya!